Hello, my name is Eric Lee, a student at Georgia Tech, and this is my digital sampling experiment for AU2610. In this project, I conducted a study on measuring the sound power decay over distance. Digital data acquisition systems allow us to measure acoustic signals with high precision. In this experiment, I explored how sound levels change with distance from a source, a principle that's important in applications like speaker design, noise control, and microphone placement. The behavior of sound, especially at high frequencies, can vary dramatically due to interference effects. This experiment aimed to quantify those effects by analyzing how the amplitude of a microphone recorded signal changes as the distance increases, and how this behavior differs from a low frequency tone at 1000 Hz and a high frequency tone at 10,000 Hz. So, some objectives. The main goals of this experiment were to characterize how sound amplitude decays over distance, to analyze the variation in microphone recorded power as the speaker and mic move apart, and to compare the decay behavior between a low frequency signal and a high frequency signal. So moving on to the approach. For this experiment, I used a LabJack T4 DAC unit connected to a microphone. I also used a 3.5mm breakout adapter and a tone generator app to produce constant tones, as well as a ruler to measure distances. For the setup, the sampling rate of the DAC was set to 22,000 samples per second, and the record length was 1,024 samples. I used a smartphone playing either a 1000 Hz or a 10,000 Hz tone at 80% volume, and the phone and microphone were kept at the same height in a quiet environment. For the procedure, for each trial, the tone was played for about 1 second at a fixed distance. I tested 6 distances in total, 0, 2, 4, 6, 8, and 10 centimeters. For each distance, I recorded the microphone's output and extracted both the time history and power spectrum using the DAC software. I identified the signal strength at the target frequency and repeated the process for both the 1000 Hz and 10,000 Hz tones. So the results. Starting with the week 2 data. So prior to beginning the experiment, I analyzed 11 audio tracks to analyze waveform behavior. Some interesting waveforms from the 11 tracks include tracks 3 and 4, which were triangle and square waves, respectively. They had a primary peak at 1000 Hz and then smaller peaks at every odd multiple. The square wave had less power than the triangle wave. Track 6 was a ramp wave that had similar behavior to the triangle wave, except the power of the peaks changed over time. Track 7 and 8 were the noisy sine waves, and they characterized white noise. Track 10 was a product of 2 sine waves with 2 visible peaks at 1000 plus minus 100 Hz. Track 11 was a sine wave of a sine wave, where the frequency of the peak oscillated between 0 and 1050 Hz. Moving on to the mic validation. In addition, before beginning the main experiment, I validated the microphone's frequency response by comparing signal levels at known tone frequencies between a direct DAC connection and the mic setup. The relative response ratio ranged from 0.13 to 4.0, which demonstrates that some frequencies were captured better than others, and this validation ensured that the mic behaved consistently across the frequencies of interest. So here are tables 1 and 2 showing the VRMS and the dBVRMS values for the 1000 Hz and 10,000 Hz tones at each distance. You can see a clear and consistent drop-off in signal strength for 1000 Hz, while the 10,000 Hz results are more erratic. For figure 1, it shows that the signal level in dBVRMS for both tones across distance, and the 1000 Hz data shows a clear linear trend, while the 10,000 Hz data fluctuates, possibly due to interference and near-field effects. Figure 2 plots the signal amplitude in VRMS versus distance, and the 1000 Hz data again shows smooth exponential decay, while the 10,000 Hz tone behaves inconsistently. These results reinforce that lower frequencies are more stable for measurements in small-scale environments. Some complications. One major complication occurred with the 10,000 Hz tone. Instead of decreasing steadily, the signal increased between 0 and 4 centimeters, then fluctuated. The trend line R squared was very low, indicating poor fit. Possible causes are near-field effects arise due to short wavelengths. Constructive and destructive interference creates pressure variations that impact measurements, and reflections from nearby surfaces distort the microphone's received signal. So some strategies to mitigate this in future testing. I would increase the minimum measurement distance beyond 1 wavelength and also conduct tests in an acoustically treated room to reduce reflections. So, success criteria. The goal of this experiment was to measure how sound signal strength changes with distance using a DAC and microphone system. Success was defined by four key criteria. First, the system needed to accurately capture the signal amplitude at both 1000 Hz and 10,000 Hz. Second, I expected to see a clear decrease in signal strength with increasing distance. Third, the 1000 Hz results needed to show predictable behavior that aligns with acoustic theory. And finally, I aimed to identify and explain irregularities in the 10,000 Hz data, such as interference or near field effects. So some conclusions. In conclusion, the 1000 Hz signal behaved as expected, showing strong predictable exponential decay with distance. The 10,000 Hz signal was much more variable, largely due to interference in near field pressure effects. Lower frequencies proved more reliable for analyzing sound attenuation, and this experiment highlighted the importance of considering frequency content, mic placement, and environmental conditions when performing acoustic measurements.